Write the first trigonometric function in terms of a second for theta in the given quadrant. So in quadrant one, in quadrant one, everything is positive, right? So that's actually a benefit to us. So we're going to write secant in terms of sine. So secant in terms of sine. So secant theta is going to be solved for. Okay. Now we have to think of a relationship that involves secant and sine. Okay. And as we think through, or we even look through our table that we introduced yesterday, or not yesterday, but maybe 2 days ago, that had our fundamental identities in it, none of these relate secant directly to sine, do they? Okay, but that doesn't mean that you can't get there, okay? So let's say that we've used the transitive property before, correct? Let's say that Mr. Fay is related to Colin, but Colin is related to Canyon. Could we make the link then that Mr. Fay would be related to Canyon, even though I didn't maybe know at the onset? Does that make sense? So same idea here, okay? I don't have a direct link from secant straight to sine, but I do have a direct link from secant to cosine, don't I? And yesterday, we also saw that there's a link from cosine to sine, right? The link from cosine to sine is this one, okay? So in practice, a lot of these actually involve us using multiple identities. It's actually, after we do a lot of these and kind of maybe categorize them, it's actually very rare that you make one substitution and you're there, okay? We're going to do multiple substitutions. So right now we know secant is equal to 1 over cosine, okay? But like the problem says, we don't want cosine, we want sine. So we want everything that's on the right-hand side here to change to sine. So the way we can do that is that we take the relationship that cosine squared x plus sine squared x is equal to 1. If I solve for cosine, I get cosine squared x equals 1 minus sine squared x. And then cosine x is equal to plus or minus root 1 minus sine squared x. Is it okay? So whenever you want to change sine and cosine in and out, okay, we've done this maybe 2 or 3 times now. If you want to replace cosine, this is how, with sine, this is how you're going to do it. If you want to replace sine with cosine, you would do the same procedure, but you would solve for sine instead. Does that make sense? So now I can make that change. I can come over here and say secant of theta is equal to 1 over interchange cosine. I'm using x. It doesn't really matter, the variable. I should have said theta here, but it doesn't matter. So that's going to be plus or minus, and now 1 minus sine squared theta. Okay. Once you do that, the reason they ask you that theta is in quadrant 1 is for us to decide which of these that we have to use. Okay. So what you do is, okay, if we're looking at secant is what kind of number in quadrant 1? Positive. Meaning that this quantity over here needs to also be positive if these things are going to equate to one another. So obviously 1 is always positive. This denominator, how am I going to make the denominator positive? I'm going to have to choose the positive version, right? And there we have secant theta is equal to the same thing as 1 over square root of 1 minus sine squared theta. Okay. One way that, and I think it's obviously if you're going to use your TIA 384 to check these, that is a nightmare. Okay. Because your TIA 384 does not have a secant, cosecant, cotangent on it. You actually have to use 1 over sine, 1 over cosine, and 1 over tangent to do that. Graphing these on your TIA 384 is not all that enjoyable either. Okay, you got to mess around with the window. You got to mess around with the mode that you're in, all that kind of stuff. So what I like to do is I like to just jump to Desmos. It's the best graphing tool, I think, to show the trigonometric functions. Okay, so I'm going to type in just secant of x. Okay, and then I'm going to type in 1 over the square root of 1 minus sine squared of x. And we see that right now they are overlapping only at the top, right? Okay. But what we were interested in was, were these things the same in the first quadrant from 0 to 90? Does that make sense? So what I'm going to do right here is I'm going to go between 0 and 90, but the way that Desmos is set up, right now it's in radians, so I'm just going to go between 0 and pi over 2. So really all I'm interested in is looking at, are these two things the same in that red region? Does that make sense? And if I toggle them on and off, can you see the black overlapping the purple in that red region? Does that kind of make sense? Okay. So they are indeed the same in the first quadrant written in this format. Okay. They're not the same everywhere. Okay. But in the first quadrant they are. Okay. And actually, if I go from negative pi over 2, so negative 90 degrees to positive 90 degrees, they are also identical. So this would be 0 to 90 is first quadrant, right? Negative 90 to 0 is actually, if we change it to positive angles, it's 270 to 360. So this would be representing the fourth and first quadrants. Okay, so these two things are identical in the first and fourth quadrants. Does that kind of make sense on how to do that? Want to do another one? 33? All right, so let's find the values of the trigonometric functions for theta from the given information. So we know we got sine theta is negative 12/13. Theta is in quadrant 4. So I'm going to draw a picture of theta. So that purple angle is theta, terminating the fourth quadrant. Okay. So we're going to draw any triangle. I like to just make it big enough to where I can work here. I don't want to make my triangle real tiny like that. Draw that out and draw straight up to the x-axis so that we get our right triangle here. Okay. And what we talked about yesterday was, if we can learn everything we need to about this right triangle, that will tell us everything that we need to know about theta. Okay, so right now they're saying theta is, or sine of theta is negative 12/13. So that is theta. Remember, we've been calling this angle here kind of like theta bar, right? Okay, but that, if I can learn something about that green angle, or everything that I know about that green angle is the same, then I'm going to need to know about this purple angle theta. Okay, so When it says sine of theta is equal to negative 12/13, that means the opposite side is the 12, and the hypotenuse is our 13. Now this 12, because, so remember what we're doing here. We're in the quadrant, or the coordinate plane, okay? So if I want to be at 0, 0, and I want to get down to that point right there, I have to go over to the right a positive and then down a negative, correct? So that 12 is actually negative 12. And that's why we see, as we go opposite over hypotenuse here, that negative is attached to the 12 for that reason. So now we're going to use the Pythagorean theorem. We need to find that distance right there. So we should call that x. So we'll say x squared plus negative 12 squared should equal 13 squared. So x squared plus 144 equals 169. X squared is 25. So x is plus or minus 5 using the Pythagorean theorem. But because it's a distance and it's to the right from 0, 0, I'm going to say that distance is 5. Is that okay? So now when it wants cosine, remember cosine of theta is x over r, or adjacent divided by hypotenuse. Sine we already have, but we can confirm that it's y over r in this case, or opposite over hypotenuse. Tangent is going to be y over x, or opposite over adjacent. And then we can find the other three by taking those reciprocals. So when it says cosine theta is x over r, we just said x was 5, r was 13, so that's where we're getting our 5/13 there. Sine we already had. Tangent is y over x. So y is negative 12. X is 5. So that's where we're getting our negative 12/5. And then if I know cosecant and sine are related to one another, I just find the reciprocal of the one they gave me, so negative 13/12. Secant and cosine are related to one another. They're reciprocal, so 13/5. And then cotangent and tangent, so I should have negative 5/12. Now we talked yesterday how we can check this, and this is I think the check is actually more important than actually doing the work to get these answers. We said yesterday if we take the sine inverse of this negative 12/13, okay, we get something like that. Now that's in radians, so let's go ahead and put this in degrees. I get that number right there. Okay, so, and you could do it this way with the negative. I don't like the negative, so the negative 67 is saying, let's see here, negative 67 degrees that I'm getting from my calculator, and we'll talk about why it's giving a negative eventually. But it's this angle right there, as if I were to go in the clockwise rotation. Does that make sense? Well, theta, if we always think about theta being that angle there, okay, those two angles should add up to 360, right? Okay, so if this is a negative angle, and I don't like working with negative angles, I can add 360 to it, and now I have a 292 angle. Does that make sense? And 292 is indeed in the fourth quadrant. So that is when they say sine of theta equals negative 12/13. That means to me that every angle, or every angle of 292.619 degrees, or every triangle that has essentially that 67-degree angle is going to have a 12/13 relationship of the opposite side divided by its hypotenuse. Okay. But if I just, for instance, if I type in, just let's call this angle here, I think there's a theta key here. Can we do that? Can we define it that way? Oh, nope. We'll just say T equals. So T equals that, and if I go sine of T, it gives me that right there, which is negative 12 divided by 13. Does that make sense? Okay. So we know right now, based off of this, that we currently know what theta is. Okay. So how can I use this to determine what cosine is? Okay. So whether I've got this correct cosine value of 5/13. Well, 5/13 is 0.3846. If I take cosine of T, does it give me the same 3.846? Does that make sense? So because I'm able to find out what theta really is here, it can allow me to confirm that that is indeed the right value for the adjacent side divided by the hypotenuse. Doing the same thing then for like secant. Secant we said should be 13/5. That is 13/5. Okay, 2.6. 13 divided by 5, 2.6. And we can do that for all of them. When they ask you, when they give you a trig ratio for one of the trig functions, then they're asking you to draw the triangle essentially. Use the Pythagorean theorem to find the missing part. Now that you have the missing leg, here was 5 for us, we should be able to look at SOHCAHTOA and find the other ratios. Does that help? Any others? Last one? So here they're saying if theta is pi/3, find the value of each expression. There's a couple different ways we can do this. Let's approach this not in radians first, and then we'll come back and do it in radians. So when it says pi/3, does anybody remember how many degrees pi/3 is? Or if you don't remember, it is 60. We can go pi/3 times 180 over pi. That's the conversion factor. Pi's cancel. 180 divided by 3, 60 degrees. So instead of saying theta equals pi/3, let's do this with, because I think, at least if I were in your shoes, I would rather do things because angles make more sense to me as degrees initially. So I'm going to do this in 60 degrees, and we'll come back and see if we can do the same thing then in radians. If theta is 60 degrees, find the value of each expression. Well, when it says then sine of 2 theta, well, we just said theta was 60 degrees, right? So we're really asking what is the sine of 120. Does that make sense to everybody? So this goes back then to the idea, if I'm looking at an angle of 120 degrees, that's going to come over here. I'm just going to write 2 theta equals 120 here. Okay, so I'm interested in that green angle there. Okay, but that green angle is bigger than 90 degrees, so I don't really want to use that. I'm going to come back here. I'm going to draw that down. Get this red triangle here, and this angle right there, that angle right there, is going to be how big? 60 degrees. Remember, that's what we call theta bar. That's our reference angle. Now, you don't always have to redraw this, but usually when we talk about theta bar, it's going to end up always being between 0 and 90. So it comes to a first quadrant angle. If this is 60 degrees, it's a right triangle. That's going to be n. That's going to be n radical 3, and that's going to be 2n, correct? So when they ask us to find the sine of, in this case, 120, it's going to be the same thing for us as the sine of 60 based off of this reference angle. So sine of 60 then is opposite over hypotenuse. So n radical 3 over 2n, n's cancel, and it leaves me with that. Okay? Now, the only difference between a theta and a theta bar is going to be the plus or minus aspect, or could be the plus or minus aspect. Okay? So, in this situation, our sine of 120 and our sine of 60 are going to be identical, but we have to pay attention to the plus or minus. Is the sine of 120 positive or negative? It's positive, because it's in the second quadrant. Okay? Because remember, the sine, S-I-N-E, is the y value of any point, essentially, on that terminating ray divided by the length of that then terminating ray, right? Well, any y value that is, so the terminating ray is always r, and that's always positive. Any y value in the second quadrant is positive as well. So whenever you're in the first or second quadrant, your y value or your sine is always going to be positive. So that's why we get this radical 3 over 2. Okay. That being the case, if it says sine of theta times 8, so sine theta, again, back to the original condition, was 60 degrees. Well, we just figured out sine of 60 was radical 3 over 2, right? Okay. Well, this 8, remember what this is. So sine of 60 is a symbol for another number. Does that make sense? Sine of 60 is a symbol for radical 3 over 2. This 8 is a multiplier out in front of that. So think 8 radical 3 over 2, doesn't that reduce to 4 radical 3? There will be eventually other ways of dealing. This is referred to as a double angle, because theta is our angle and the 2 doubles it. So there may be easier ways down the road with some what we call double angle formulas that will allow us to do this as well. At the beginning, we said let's change this to degrees and then come back and do it in radians. Because we never had to go back into radians for my answer, right? I don't think going back to this again and leaving theta as pi over 3 is going to be of any benefit. Okay? Because we didn't need radians anyways, right? Does that make sense? So sometimes radians, when you change them to degrees, you can do all the work in degrees and then come back and have to change them into radians. This one we did all the work in degrees, and then our answer was just the ratio of opposite sides and hypotenuses. So never had the purpose or the need, I guess, to change back to radians. So does that kind of make sense? Anything else? We can do anything. 30? Was the first one we did. Yeah. Let's do 31 if it's similar, or we can do 31 and 32. I think we're going to be benefited by going over as many of these as we can. All right, so it says write the first trig function in terms of the second one. We got secant in terms of tangent. Secant in terms of tangent. Going back to, I think this was going to be a little bit easier than the first one we did. Are there any in here that relate secant and tangent directly? None of these do, right? Is that one? That has secant and tangent directly in it, right? And those are the only ones that are in there. So we should be able to say tangent squared theta plus 1 equals secant squared theta. Okay. Now we're going to be in quadrant 4, so that'll be something to think about here in a moment. But we're going to solve for secant. So to solve for secant, don't I just have to take square root? So this will be secant theta equals plus or minus the square root of tangent squared theta plus 1. Now because we're in quadrant 4, cosine is positive in quadrant 4. So if cosine is positive in quadrant 4, why is secant also positive in quadrant 4? Yeah, because they're reciprocals of one another, right? Okay. So secant and cosine are reciprocals. So cosine's positive, so is secant. So if secant's going to be positive in the fourth quadrant, what kind of number does that have to be in the fourth quadrant? We also want that to be positive, right? Because if it's not positive, then that equality would not exist. They'd be opposites. So we want the positive version. So secant theta equals tangent squared plus 1. The whole dynamics of the problem change when they ask us to put it maybe in, let's say we put it in the third quadrant. So theta being in the third quadrant, now tangent is the only one that is positive, right? So if tangent's the only one that's positive, that would mean that this number right here, if theta was a third quadrant angle, when I put theta in there for a secant, it would actually make this negative. Does that make sense? Even though there's no negative sign here on this symbol, remember this is a symbol for another number, that other number would actually be negative. Okay? Type in any number between 0 and 90 for the secant. So secant of t, and let's let t go between I don't know why I said 0 and 90, but we're going to go between 180 and 270. That'd be the third quadrant. No matter what I do, that number, you can see it right there, that number is always going to be negative, right? Does that make sense? Okay. So this is negative, so then to make this a true equation, that needs to be negative 2. So we can change the problem in its entirety, and it's just flipping the plus or minus aspect of it. But just by changing the quadrant, we can garner different answers. (32) is the same idea. It says cosecant and cotangent. Cosecant and cotangent. If we go back to this here, does this relate cosecant and cotangent? So we can take square root of both sides and get the cosecant solved for in terms of cotangent. And then decide what quadrant we have to be in. Anything else? Say again? 9C. Okay, so if we've got 23 pi over 7, so they want us to find the reference angle. So when they give these to us in terms of theta, so these are in radians, it's actually very rare that we're going to actually stay with like 0, 2 pi, pi, pi over 2, and 3 pi over 2. Because when they change the denominator to 7, that becomes hard to compare, where if everything's in like different denominators, uncommon denominators, it's hard to decide where 23 pi over 7 is. So what I'm going to do is I'm going to rewrite this as 7 pi over 7. Is that okay? Is that still pi? Then this would be 14 pi over 7. Halfway between 0 and 7 is 3.5, so I'll just call this 3.5 pi over 7. And then this would be just basically, so 0 to 3.5, add 3.5, I get to 7, add 3.5, I should get to 10.5 pi over 7. Does that kind of make sense on how I get those positions? Now the reason I do that is because I see that 23 pi over 7 is greater than 2 pi. So I don't like dealing with a theta that is bigger than 2 pi. So what we're going to do is start subtracting multiples of 2 pi. So I'm going to write it this way first. Subtract multiples of 2 pi. I'll just put k there to represent the multiples. But again, if I'm going to subtract 2 pi, I got to have a common denominator, so it's going to be actually 14 pi. Okay, and what I have to do here is I actually only have to subtract one multiple of 14 pi, right? Because what's 23 minus 14? 9, right? So I get 9 pi over 7. So 9 pi over 7 is coterminal with 23 pi over 7. Does that make sense? If I were to trace out 23 pi over 7 and then trace out 9 pi over 7, even though they're different sized angles, they start and stop at the same positions. I like 9 pi over 7 because 9 pi over 7 is between 0 and 2 pi, or between 0 and 14 pi over 7. Okay? So now when I draw my angle here for 9 pi over 7, I know it should stop in the third quadrant. Does that make sense? Okay? Because this here, this is the reason I wrote that right there. That's 10.5 pi over 7. 9 pi over 7 should be short of that. So now if I want my reference angle, remember my reference angle is this blue angle right here. Okay? So if this pink or purple, whatever color this is, if this angle here was 9 pi over 7, how many degrees do I need to work back, or not degrees, but how many radians do I need to work back to get to 7 pi over 7? Is it 2 pi over 7? Does that make sense? Okay. Another way of doing that is we talked that if we have I'll just draw a different coordinate plane here. If your theta and theta bar, or theta resides in the first quadrant, then theta and theta bar are the same. If theta resides in the second quadrant, or terminates the second quadrant, then theta bar is equal to 180 minus theta. But if we do it in degrees, it's pi minus theta. In the third quadrant, it is theta minus pi. And that's the one we're working at here. Our theta was 9 pi over 7. Subtract pi from that, which is 7 pi over 7. 9 pi over 7 minus 7 pi over 7 gives me that there. So if you want to use a formula to generate that, you can. Here, theta bar would actually be, if I'm in the third quadrant, it is 2 pi minus theta. There was one on there. I know somebody asked me yesterday at the end of the third period. It was talking about reference angles. Maybe it's question 10. Yes. Now okay, let's do question 11 real quick. Same idea as 10. So find the reference angle for the given angle. So if I've got 2.5 pi, so there's 0, there's 2 pi, here would be pi, here's 1.5 pi. I think it's actually like 1.57 pi. And this is like 4.57 pi or something like that. Or 3. I don't know why I said 7 there. This is 3. Pi over 2, let's see what, I think it's 1.7 or 1.57. So pi over 2, 1.57, okay. And then 3 pi divided by 2, 4.7, okay. So if we multiply pi through, those are the values for those, okay? Or if I leave it as, pi over 2, it's 0.5 pi, and this would be 1.5 pi. Does that make sense if I don't multiply the pi through? So if it wants 2.5 pi, I'm going to go 1 revolution around. There'd be 2 pi, right? Okay. And then this is to there, that'd be 2.5 pi. Which now, if I want if you ever get a quadrantal angle here, like we have, then you're basically just going to take that y-axis, and how many degrees or how many radians do I need to take that y-axis to get back down to the x-axis? It would be that 0.5 pi. Does that make sense? It's kind of a unique situation there. Now, the real reason I want to do this question is because of that one right there. It's 2.5. Well, that means that the pi has already been multiplied through. So I'm going to be looking now at numbers like this, where that's 3.14, 6.28, it's 1.57, 4.7. I've got the pi already been multiplied through these values. Does that make sense? And now they're written as rounded irrational values. So if I'm at 2.5, well, 2.5 would terminate in the second quadrant, maybe about right there. That would be theta. So theta bar then is going to be that angle there. Well, in order to get that angle, it's going to be 3.14 minus 2.5. So instead of 3.14, though, they want you to use pi. And just say pi minus 2.5 and write it as an exact value there. No new homework tonight on, what is tomorrow? Tomorrow's Thursday. So tomorrow we will start section 5.4, talk about inverses. Thank you, too. Ari has a question that says, and this is we haven't talked about this, and it's a great question. Let's say that I've got maybe they want to know what is the, let's say, sine of, this is usually something we don't necessarily do, but let's say they say that they want to know the sine of 270 degrees, okay? Or they want to know the cosine of 270, or they want to know the tangent of 270, okay? What I'm going to do is I'm going to draw out 270 real quick, and I get to right there, correct? Okay. 270, anything that's a multiple of 90 is referred to as a quadrantal angle. Okay. Now, what stinks about this is that when we talk about like reference angles and all that kind of stuff, we like to, if I had something that stopped in the third quadrant, I like to draw that triangle right there, correct? Okay. I like to draw a triangle that goes back up to the x-axis. I'm going to do that here at 270, but I'm going to take some liberty. I'm going to draw the picture. I'm going to draw a triangle here. Kind of stinks. Let's see here. Try to get you a better. Okay, so remember theta was 270. It was going up to that, okay? Now, if in reality, there is no triangle there. Does that make sense? In reality, there is no triangle that I could do that because I would be just drawing back straight up the y-axis. Does that make sense? Okay? But I'm taking some liberties here and drawing this triangle. I think this will make more sense when we start putting values in here, okay? If I go to 270, if my theta is 270, I want to figure out what theta bar is and all that kind of stuff, or I want to find out sine of 270, cosine of 270, tan of 270. This distance here to there would actually be 0. Does that make sense? Okay. Now, if that's 0, then that would actually be a collapsed triangle, correct? It would not exist. It'd be just a vertical line that is the negative y-axis, okay? But if that is 0, okay, we are going to use our, let's use our, like, sine squared theta plus cosine squared theta equals 1 relationship, okay? If right now I've got cosine being 0 there, right? Okay. So that go away, and it would give me sine to be 1. So this would actually be 1, and my hypotenuse would be 1. And that doesn't make any sense for a triangle, correct? I can't have a side that is 0, a leg that is 1, and then a hypotenuse also be 1. Okay, that triangle would not really exist in reality. But it's the only way that I can draw it to hopefully maybe make some sense of what sine of 270 is, what cosine of 270 is based off of SOHCAHTOA. If I'm looking at a triangle right now in this, so now I'm just extending this triangle and making it a little bit bigger so I can do the work. That's my right triangle, and you're interested in that angle right there. And I ask you, well, what is the sine of 270? Okay, now this number here would be negative, right? Because we're in the third quadrant. Okay, so this is negative. If I said sine of 270 here, you would say negative 1 over 1, right? Does that make sense? If I type in sine of 270, does it give you negative 1? Okay. Cosine of 270 would be adjacent divided by hypotenuse, would be 0 over 1. If you type in cosine of 270 should give you 0. Okay? What's tangent going to give me of 270? I go opposite over adjacent. Undefined. Okay? Tangent 270 undefined. Right now, with what we call the triangle approach to trigonometry, or the right triangle approach, these quadrantal angles are not as easy to discuss as they will be when we get to Chapter 6. Basically, what we find out in Chapter 6, to give you a little bit of a preview of that, is that these triangles that we like to talk about, these right triangles that can be of any size, we diminish the radius or the hypotenuse of those right triangles, and we force it to be 1. Okay? And when it becomes 1, so when R is 1, and we have this point here, x comma y, okay, where this is x and that's y, and I asked you something about theta, okay? Well, if I asked you the sine of theta, and you say that, well, that's y over r, and r is 1, it's just sine of theta is that y coordinate. Does that make sense? When I go cosine of theta, it's x over r, but r is 1, so I get cosine just to be x. So I get that. So what we say then, and then that's going to be true no matter where I'm at on this circle, as I rotate that terminating ray, no matter where I'm at on that, we call it the unit circle, that will be the relationship, that this number here is the cosine of the angle, and that number there is the sine of the angle. Therefore, when I get to an angle of, let's say, we'll just do 90 instead in this case. If I get to an angle of 90, so my terminating ray is there, my initial ray is there, this point right there, because I know that distance is 1, that point, because that was the length of the terminating ray, that point is 0, 1, right? So then the cosine of 90 is that 0, and the sine of 90 is that 1. Okay? Keep that process going through, and I get to 180. At 180 degrees, that ordered pair is negative 1, 0. The cosine would be negative 1. The sine would be 0. If you take your calculator and type in cosine of 180, it's going to give you that negative 1 back. That is the x-coordinate of that ordered pair. If you type in sine of 180, it's going to give you back that y-coordinate of that ordered pair of 0. And that will make it easier to, I think that's much easier to explain, because I don't have to make this kind of false triangle here and do opposite over adjacent with sides that really don't exist as a group of 3. Does that kind of answer your question? I don't know if that's the best, just because of the nature of that triangle. That's hard to explain. It's hard to see. But once we get to Chapter 6, somebody asked this in the last class as well. They asked, right now, in some of these questions that we went through in the last class, they're changing everything from degrees to radians, or radians to degrees whenever they solve them, which is fine. But her question was, will I run out of time on a test doing that? Okay. Chances are that you might. Okay. Obviously, if we are, and this is how I decide on the length of tests that I give you guys. If I write a test and I set myself up 15 minutes. If I can do that test in 15 minutes, I think you guys can do that in 3 times that amount of time. Does that make sense? Okay. So I set the test up, I write the test, but I will do that test then using the most efficient manners of getting through those problems. So I will, if it's in radians, I'll keep it in radians. If it's in degrees, I'll keep it in degrees. And I won't make that merger. Okay, I won't make that conversion. If you decide to make those conversions on tests and quizzes, that's fine, but know that that's going to eat away time that you might need devoted somewhere else. Okay, so just be on the lookout. But My argument to her was, that's fine right now. We haven't been doing a whole lot with radians and degrees. It's been mostly degrees right now. Okay, there's a few questions in the homework that deal with radians, but for the most part, instruction has been devoted towards degrees. And the reason I do that is I want to make sure that we understand the concepts before we start trying to throw stuff in there with radians and not understand concepts and not understand radians, and then we don't understand anything, right? Does that make sense? That's kind of the approach that when I was in school, my teacher, first day, these are radians, these are degrees, we're going to interchange them and never talk about it again. Okay, you're just going to have to know what they are on your own. And, you know, most of us were swimming with trying to figure out what a radian was, and then focusing on that inside problems that involved radians, there was no way we could get to the problem and understand the problem because we were so hung up on radians. So that's why I do a lot of stuff in degrees early on. When we get through Chapter 6, we'll use radians and degrees so much in Chapter 6, and we relate them back and forth so much that it's going to become second nature, that when I say 2 pi over 3, you instantly know, hey, he's talking about a 120-degree angle. When I say 5 pi over 3, you know I'm talking about a 300-degree angle. Okay? It'll be something that you can make that jump quickly like that. Does that make sense? You've heard me say the unit circle. Let's get a quick peek what that thing looks like real quick. Don't let this scare you. It's pretty easy to develop. You already know all the things. And can you guys count to 12? Can't count to 12? Okay. Can you count to 360 by 30s? Okay, you can do that. Good. Don't know why you can't count to 12 then. If you can do those things, you can create the unit circle. Okay? So the unit circle is this thing here. Get a good picture of it. Which now, it's just right now, it's all written in radians, but pi over 6 is 30 degrees. Okay? And going off the logic we just talked about, there's an ordered pair there on that unit. So that circle right there is a circle of radius 1. There's a point on it. If I were to trace out an arc of 30 degrees, okay, or pi over 6 radians, there's a point that resides on the circumference of that circle inside the coordinate plane, and that point is located at the ordered pair radical 3 halves, comma 1 half. If I were to type in what is the cosine of pi over 6 or the cosine of 30, my calculator is going to spit back 0.866 because that is radical 3 over 2. It's the x-coordinate of that ordered pair up there. If I ask the sine of pi over 6 or sine of 30, my calculator is going to spit back the y value of that ordered pair, which is 1 half. Okay? So we'll use that so often. And the one that we develop, it'll say pi over 6, and it'll also say 30 right next to it. And you'll just use this so much that you'll see those so often together, and you'll just associate one with the other. Does that make sense? When I ask, the way we create this, I ask, can you count to 12? Because this essentially goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And it gets me all the way around by counting. What I was doing was counting multiples of 30 there, up to 360, but it was essentially 1 through 12, because 12 pi over 6 gets me from 0 to 2 pi. So that's a lot, and we'll develop that and create that in probably about a week. But I show that usually every year, and people get flipped out, wigged out, and there's a lot of stuff there. It's crazy. Has anybody in physics used that yet? You have used it in physics? Okay. If you've used it in physics and never been taught like what it is, I've had people in the past in physics say, he made us use the unit circle. He didn't even talk about it. It's coming in the next couple of days, and it will make a whole lot of sense and be very, very easy for you to use. And basically, what it is it's a calculator for us. Okay, it's a reference for finding sine, cosine, tangent values very quickly. So Good question. Any other questions? Anything you guys want to talk about homework-wise? Just questions in general? Anything so far about Chapter 5? 5.3's homework. Last class, all we did was we went over 5.3 homework. What do you guys want to do? Got 5.3 homework all done, Andrew? You got any questions over it? So let's just sit in silence then and not ask him. That's probably the best approach. Why? Is somebody else's performance directly linked to your performance? Huh? No, it doesn't. Unless they're cheating off you. Anybody? Jackson got them all? Aced it? I know. You're right. Okay, so we've got question 30 and 31, very similar. And I'm going to change it a little bit. Let's put this in quadrant 2. Because in quadrant 1, everything's positive, right? So doesn't always if we were to do every example or every question in quadrant 1, we don't get the little caveat that we need to understand in regards to choosing the correct plus or minus sign in some of these because they're always positive in the first quadrant. So procedure is sometimes missed because of that quadrant 1. All right, so if we go back to our chart, go back to this thing here, okay? And right now, guys, use that as a reference, okay? Have your notes out, put those at the top of the paper, whatever you might need to do, but the goal eventually is that those things are committed to memory. But the more you write them down, okay, writing something down one time is 6 times more effective than hearing it or saying it to yourself, okay? So write these things down as much as you can, and then they will embed themselves in your memory, and you'll be able to do these things much quicker, okay? We want to write the first one in terms of that one, so meaning that secant theta is going to be solved for, it's going to be isolated all by itself. It will equal something. It'll be a lot of garbage on the right-hand side. But of all that garbage, the only trig function I should see is sine. Okay, that's what this is saying. When I go through here, and what is the issue? I look at sine. That relates to cosecant. That's not secant and sine, right? Here's secant, but that goes to cosine. That's not a direct link to sine. Not a direct link, not a direct link. That deals with sine, but nothing with secant. That's cosine in there. Nope. These don't either, right? Okay, here's secant. Now sine is in here, but it's really not clean. I'll put a star on that just to prove a point in a little bit. We're going to use that one. Okay, and here's the idea. Let's say that I know that I am related to Mikey. Okay. Let's say Mike knows that he's related to Ty. But I don't know that Mike's related to Ty. Meaning that I don't know that I'm related to Ty, though, right? Does that make sense? But if I'm related to Mike and Mike's related to Ty, transitive property says Mr. Fay is related to Ty, right? Okay. There is not a direct link from secant to sine. But there's a direct link between secant and cosine, right? Nope. Yeah, maybe. That's not the best thing to do. No, because you're trying to say cosine and sine aren't related as reciprocals. They're related as cofunctions, so we could do something with that, but that'll be chapters 6 and 7. The link is I know secant is related to cosine, right? Does this right here relate cosine to sine? Yes. Okay? So you have to use multiple substitutions here is what I'm trying to get at. Okay? And it's essentially kind of the transitive property with substitutions. And in general, when we do problems like these, and these are going to be pervasive throughout the rest of the course, every chapter is going to have some aspect like this. We are going to generally make 2 to 3 to 4 substitutions throughout a problem to link one thing to a second to a third, and now we'll get my first thing linked to the third thing, or my first thing linked to the fourth thing. Okay? So that's what we're going to start with, is secant theta equals 1 over cosine. Okay? Now, what we are going to do is try to, because this doesn't get to what we want the right-hand side to only have sine in it. So now we're going to look at the right-hand side and say, okay, can I get that replaced so that it only says sine? If you think about this, this is ultimately a problem we've already done. How do I write cosine in terms of sine then? Is basically what's being asked here now. Does that make sense? So I got cosine squared theta plus sine squared theta equals 1. Can you solve that for cosine? So cosine squared theta equals 1 minus sine squared theta, square root. Can I get that, right? Now, you can make the substitution. You can replace that green thing with plus or minus square root of 1 minus sine squared. So secant theta, 1 over plus or minus 1 minus sine squared theta. Okay? Now, just got to remember, what quadrant were we in? 2. Because here's the thing. If I graph these things, and I know that we haven't looked at what a graph of any of our trig functions are yet, okay? But that shouldn't matter if we understand that when we write an equation, that the left-hand side is a graph. We talked about this in Algebra 1. The left-hand side is a graph. The right-hand side is a graph. And the solutions that satisfy the equation are where those graphs intersect, right? So I don't care if I don't know how to graph a secant. The technology is going to do that for me. Here's the secant of x. I never knew it, didn't know how to do it, but the technology does. Okay? And now I also know that 1 divided by, if I just type in the square root of, what was it, 1 minus sine squared x. Looks like that. But I also need the negative portion of that, right? Because we just had a plus or minus, correct? Control Z, Control V, put a minus here. Okay? So the red one, the left-hand side that we are trying to isolate, secant theta, we're trying to rewrite it in terms of those. That is the plus or minus thing that we had, right? What we see at the red one is only, I wish I could bring that to the front, but can you guys see? That's kind of hard to see. Change colors here real quick. Maybe. That might be better. Got them. Okay. All right, so the dotted ones are the plus or minus, right? Okay. Secant is the solid ones. Okay, they're not always 100% equivalent, right? Okay, we've got some issues going on here. So what they're going to say is, if I want them to be equal, we have to look at a certain quadrant, because sometimes they're not going to be equal. And the places that they're not equal, they're just opposites of one another. Okay? But right now, what I want to think about is, if we're in quadrant 2, if theta ends in quadrant 2 like this, is the secant positive or negative in quadrant 2? What is the reciprocal of secant? Cosine. Okay? So if I know where cosine is positive or negative, I should also know where secant is positive or negative, right? So cosine is negative in quadrant 2, because all students take calculus, right? Okay? In this quadrant, we would have, looking at this triangle here, this distance here would be the adjacent side, so that's going to be negative, and r is going to be positive. You're terminating your raised length. So cosine of that angle would be adjacent, a negative, divided by hypotenuse, a positive, so you get cosine to be negative. So secant is also negative in the second quadrant. Okay? So this right here is a negative number. Therefore, to make this a true equation, this has to be what kind of number? This has to be a negative number. So the 1 is always positive right here, right? The denominator, the square root of this will always be, okay, thinking about sine. So sine, I don't know if we talked about this yesterday, sine and cosine, no matter what, it's always either an adjacent side or an opposite side divided by a hypotenuse, right? In a right triangle, what is the largest side of the right triangle always? Hypotenuse. So you're always dividing a smaller number by a bigger number. Does that make sense? With sine and cosine. So when you take a small number divided by a bigger number, you always get a number between 0 and 1, right? Okay? So when I take a number between 0 and 1 and I square it, it gets smaller. Does that make sense? Okay? So I'm always going to have 1 minus a number that I know is smaller than 1. So this number underneath the radical is always going to be a positive value. Does that make sense? So I'm going to, in order to get this then denominator to be negative, so my overall quotient is negative, I have to choose just the negative sign. Okay? So that's how I would type my answer in that if I was interested in quadrant 2. Okay? Look at the graph then. If I choose the negative version, okay, does the black one and the green one, do they always overlap 100%? No. What quadrant are we interested in, though? Second quadrant. Second quadrant, now the way this is set up, I think I want to do it in radians. Yes, radians. So second quadrant is pi over 2 radians to pi radians. 90 degrees to 180 degrees, right? So I'm looking inside this purple region. Would you guys agree inside this purple region that the green and black graph are 100% the same? Okay, so that's what we're getting at. If I go from pi over 2 to 3 pi over 2, so I'm going from 90 degrees to 270 degrees. So I'm looking at second quadrant and third quadrant essentially, right? Are these two things identical in the second and third quadrants? Yeah, okay. So you would have the same answer. You would have the same answer here if it says quadrant 2 or if it would say quadrant 3. Okay. Therefore then, in quadrant 1 and quadrant 4, they must be positive, and you have the positive version. Does that make sense? Okay. Other questions? I think the other ones I asked you to do that with on the assignment, like around 30. 31 was similar, right? But 31 uses is there a direct link to secant and tangent? If I go back to our table, there's a direct link here between secant and tangent, right? So I don't have to make an extra substitution. Okay. And I think 32 asks you to do a link between cotangent and cosecant. So I just grab that one, and I don't have to make an extra substitution. Okay. I told you that we were going to. I wanted to look at this one real quick, just to prove a point. Because you might do something different than your neighbor, but both arrive at things that are legitimately both correct. So let's say I have tangent squared theta plus 1 equals secant squared theta. Some people might have chose that and said, I'm going to use that thing to solve for secant. So how would I solve for secant here? Square root both sides. So I could say secant theta is equal to plus or minus, okay, tangent squared theta plus 1. Okay. Now I can't take the square root of that tangent because that's a sum underneath the radical, right? Okay. And I haven't answered the question because what did it want? I wanted it in terms of sine, right? But let's ask this question: isn't tangent squared the same thing as sine squared over cosine squared? Okay, so secant theta equals plus or minus sine squared theta over cosine squared theta plus 1 now, right? Okay, let's say the exact same thing now. Okay, but we didn't want cosine in there, correct? Okay, we got a formula. We got that cosine squared theta plus sine squared theta equals 1, right? So can't I write sine squared theta? Actually, I'd write this cosine squared theta equals 1 minus sine squared theta. Okay. So secant theta equals plus or minus sine squared theta over 1 minus sine squared theta plus 1. And that might look completely different than this right now, correct? Well, let's try something here. We've got two fractions here, correct? Okay. Can I combine those into one fraction? Okay, what would I need to combine them into one fraction? Common denominator. What's my common denominator between this fraction here and that fraction there? So I multiply the bottom there by that. I multiply the top by it. Correct? So then you can merge those. So now you can say that secant theta equals plus or minus. I'm going to be deliberate here. Rewriting just this top, be 1 minus sine squared theta, right? Over 1 minus sine squared theta. Is that okay with everybody? Okay. So then secant theta equals plus or minus. What's this numerator going to turn into? 1 over then 1 minus sine squared theta, right? Okay. Is that a fraction underneath the radical? Can you rewrite that as a root of a fraction is equal to the fraction of the roots? Does that make sense? So can I rewrite this as plus or minus radical 1 over plus or minus 1 minus sine squared theta? Okay. Does it get me the same thing as before? Would you agree that that route is much lengthier and takes a lot more kind of an understanding of my trig relationships, a greater understanding of my algebra concepts and how to navigate through those? But what I'm trying to get at here is that there is not always one pathway that's going to get you to where you need to be. Okay, I would argue that there's usually probably a most efficient pathway, but But there will be times where you choose the incorrect one in regards to efficiency, but still get to the right answer. Okay. This whole thing right here, I know that's messy, and if that blew over the top of your head right now, that's fine. But chapter 7, we will do quite a bit of this kind of thing in chapter 7. This will actually be kind of an easier problem in chapter 7. Okay, one of the easier problems we do in chapter 7. Anything else? Any other? I saw a question. I want to talk about. Go ahead, Jimmy. 35 double angle. All right, so okay. So theta equals pi over 3. Okay, I'm going to, just because of where we're at right now with radians and degrees, you can do this in radians, but I think you're going to be a little bit more successful if we take pi over 3 and change it to, anybody know how many degrees that is? 60 degrees. Okay, if you forget that, pi over 3 times 180 over pi, that gets me to 60. Okay. Okay, so then when it says sine of 2 theta, that is actually saying sine of 2 times theta being 60, so it's actually asking for the sine of 120, right? So this just turned into a question like at the beginning of the assignment, when it says, evaluate what the exact value of sine of 120 is. So you would take theta of 120, it's going to terminate in the second quadrant. You're going to draw down your right angle, and you're going to find this angle right here. And that angle right there is what we call theta bar, right? How big is that right angle, or that acute angle right there? 60. So then I'm going to find sine of 60. So some of you might, and it doesn't matter what quadrant, how you do this. If you want to draw on top of this image here, this image is just for me, my organization. If I draw another one, just in first quadrant, a lot of times we put theta bar in the first quadrant. So if that's 60, then that's 30, then this would be 2n, that would be n, this would be n radical 3, right? Again, not caring how big that triangle really is, because every triangle that has a 60-degree angle, the sides are going to be in that proportion to one another. So then sine is opposite over hypotenuse, so reduces radical 3 over 2. So sine of 60 is radical 3 over 2. So then the sine of 120, because of how we use reference angles, is also radical 3 over 2. But we have to decide, is it positive or negative? It's positive because the sine in the second quadrant is a positive y value divided by a positive r value. So the sine is always going to be positive in quadrant 2. Let's talk real quick. I think it's question 10 or 11. I might have posted it from the last class. Did we talk about it in the last class? If they ask something of the effect that theta equals 2.5, and they ask for theta bar, they want the reference angle, okay? What units is this theta in? Is it in degrees or radians? It's in radians. Where's the pi at? It's already factored in that 2.5. It's already been multiplied through, okay? So what I like to do in questions like this is instead of writing my, quadrantal angles in terms of pi, I like to write them with it multiplied out. So that'd be 3.14. Half of that is 1.57. This is like 4.57 or something like that. And this is obviously 6.28, right? So now when it says my radians is 2.5, Does that make sense that it's going to rest in the second quadrant? So then when I want theta bar, they're asking for that angle right there, correct? Okay, so how do I find that theta bar? Okay, so in order to find that angle, the way we've been doing it is like 180 minus whatever theta was, right? But because we're in radians, it's now pi minus whatever theta is. That's how you find theta bar in quadrant 2. So what was theta? 2.5. Okay? They do not, so the way we've got it set up, we'll want this, right? Is the way we've got it set up. But that's not exact, right? Okay? The only reason I put it in terms of like multiplying the 3.14 out is so that I knew where 2.5 stopped in reference to pi over 2, 3 pi over 2. Does that make sense? Okay. A lot of textbooks don't demonstrate that, show that, explain that. I've never had I don't know how people do it, but I always had professors that said, well, they just knew, I don't know if because before class they already knew what problems they were going to do and that kind of thing, and say, well, we know it rests in quadrant 2. Well, how do you know that? Put everything in the same units, and it makes it so much easier to reference where that should go. Okay, and that's what I always do throughout the entire course. Okay, always like to put things in use. You see this question up here? They were asking for a reference angle for theta being 24 pi over 7. Well, I think it's hard to figure out where 24 pi over 7 resides if I leave it as 0, pi over 2, pi, and 3 pi over 2, and 2 pi. So I change everything into sevenths. 0 and 2 pi go to 14 pi over 7 and 0. This turns into 3.5 pi over 7, 7 pi over 7, 10.5 pi over 7, and then it's easy to see that 24 pi over 7, which is coterminal after I take a rotation away from that, is 10 pi over 7. Now, isn't it so much easier to, and all I have to compare, because everything's in the same denominator now, all I have to do is compare 10 pi to all these numerators, and it tells me 10 pi should be short of 10.5 pi, right? So I should stop in the third quadrant, and I can find my reference angle if everything is in the same denominator. It makes just things comparable so much easier. No new homework. Start 5-4 tomorrow. See ya.